Why has PEEK material suddenly become the standard in the robotics industry? Even though its price is dozens of times that of aluminum alloy, it has become the key to cost reduction for robots. First, let's talk about what PEEK material is. PEEK, whose scientific name is Polyether ether ketone, was launched in 1978 by Imperial Chemical Industries, ICI, of the UK, a high-performance specialty plastic. It is as strong as steel, as light as plastic, heat and corrosion. Resistant, wear-resistant, and easy to process. Sounds pretty cool, right? So it has a nickname, the King of Plastics. This mainly comes from the synergistic effect of ether bonds and ketone bonds in its molecular structure. Ether bonds give it excellent toughness and corrosion resistance, while ketone bonds enhance its rigidity and heat resistance. Even so, engineers were not satisfied. They specially added carbon fiber to PEEK to create CF PEEK, which is equivalent to an enhanced version of PEEK. Its strength has been multiplied several times, and its rigidity is close to that of aerospace-grade aluminum. Precisely because of these advantages, PEEK has been favored by humanoid robots, becoming an ideal partner for improving performance and reducing mass production costs. First, let's look at PEEK components used in joint modules. Stator insulation end plates. Utilize its high-temperature resistance and high insulation properties to prevent insulation failure and short circuits caused by overheating of the motor during overload. Reducer gaskets. Take advantage of self-lubrication and low wear characteristics to greatly reduce friction loss, improving operation quietness and smoothness. Encoder brackets use low thermal conductivity and high dimensional stability to isolate heat transfer from the motor, avoiding thermal drift caused by high temperatures that affects control accuracy. It leverages high specific stiffness and vibration damping properties to reduce stress deformation and vibration transmission, ensuring stability and operational precision when the hand performs tasks. Micro-reduction gear brackets utilize shear resistance and creep resistance to maintain dimensional stability under continuous load, guaranteeing gear meshing accuracy and transmission reliability. Tactile sensor liners use low dielectric constant and high fluidity to ensure interference-free transmission of tactile signals while supporting micron-level precision molding. Next, let's look at the overall body structure. Cable routing channels utilize low friction and lightweight properties to protect the robot's internal cables, reduce motion friction loss, and significantly cut weight. Battery compartment housing uses high load-bearing capacity, high flame retardancy, low smoke, and non-toxic properties to meet structural load requirements and ensure safety for home-use robots. Foot force sensing brackets utilize fatigue resistance and impact resistance to ensure the structure does not undergo permanent deformation after millions of reciprocating movements. In summary, it can be seen that PEEK material helps robots gain muscle and lose weight to a certain extent. Okay? Next, let's focus on how PEEK enables robots to achieve mass production cost reduction. This is actually quite counterintuitive, because many people commented in my previous videos that PEEK is extremely expensive, dozens of times more expensive than aluminum alloy, so it should increase costs instead. This is actually a typical misunderstanding. People only look at the raw material price without adopting an overall engineering mindset, failing to see the cost benefits of large-scale manufacturing. PEEK's properties allow engineers to combine parts. For example, limited by processing technology, aluminum alloy originally requires multiple components such as brackets, insulation pads, and screws to be assembled. With PEEK, one-step molding is possible, reducing the number of parts. This means savings on assembly labor, supply chain management costs, and even repairs for loose screws later on, indirectly lowering costs. Fourth, the chain cost reduction of the whole machine. Another crucial point that cannot be ignored is robot weight reduction. It means comprehensive optimization of motors, batteries, and drivers. Lighter parts allow the use of smaller, cheaper motors. Smaller motors mean reduced battery capacity while maintaining the same battery life.